school. I worked in collaboration with Eric. Eric, do you want to introduce yourself?
Hello everyone, I'm on the Zoom. My name is Eric Brown. I'm a student at Keene State College.
And we worked under our advisor, Dr. Wei Lu. So, currently, in the certain situations is many nursing homes are really understaffed, and many of them report that they're always looking to hire new people, and the amount of people who need their help overpasses the number of staff that are currently there. And because of low staffing, it makes it really hard for the people, the seniors who are living in these elderly residences, to receive enough care that they need. So, and also, as well as that, some patients may not be very willing to talk about what pain they may be feeling. For example, some people might not want to bother the staff because they're so busy, and some others just might not want to be talking about it because they don't feel comfortable to. So, as well as that, traditional pain measurement methods are not concise, and everybody has their own different definition of what pain is. So, our objective was to make a machine learning model that could predict pain levels from different people as well. So, we can use electronic health records to facilitate and handle different remote health monitoring applications, to transfer data online and keep them there for different storage if we needed to. And so that way we can keep it for future reference if needed. So with facial features, we can recognize them by basing them off of different action units. Action units are another term for muscles on the face, and even our human eyes cannot easily distinguish them. Using AI and machine learning models, we can use a camera and take an image of a person and have the AI analyze it and tell us the different action units on the face and the values of them. Because of this, we can use emotion recognition models to determine these. As of right now, there aren't any pain recognition models on the market, so we can really only use what's more similar. Something that's very similar that I found was emotion. Sometimes emotions really connected with different pain levels, so I decided to go with that. And I found a few different things that I could use for it. Back to action units, I can use emotion recognition models, and we found the different parts of the face that it could recognize and the different values. Using these, we were able to determine different results based on this. So key things that we found of this work was we introduced a very innovative AI-based technology to possibly assess pain in Alzheimer's and possibly more people without needing verbal communication. The system used facial recognition models to analyze small expressions and different changes that a person has, and then we can analyze responses to different things to detect pain levels. And here's our methodology. This is how we decided to make our thing, and it's like a train base of what started first, from augmentation to extraction and to the model testing and data set processing. Eric, do you want to add anything here?
No, I think you're doing great right now.
Okay, thanks. Okay. So the data set we used was called the MINT pain data set, also known as multimodal intensity pain data set. It included color, depth, and thermal frames in each of them. Although for the most part, we used the colored ones for our experiments. We had 20 different subjects with many sweeps and a lot of images from different levels of pain. It included pain levels from 0 to 4, where each one corresponded to how much simulated pain they added. Where 0 was none, and 4 was the most that they administered. Each of the sweeps, there was around 80 sweeps for each subject, and each of them included varying amounts of pain levels, and we used that to determine and train our model, not train, but we used it to determine results and see what we can take out the information by running them through our action detectors. How they gave pain to the patients was they had a little wrist thing and they administered little shocks based on different power levels. So with dataset processing, we accurately cropped the faces using an MTCN program, and because we're creating binary classification, we combined some classes. Doing this, we dropped sequences from pain levels 1 and 2, and we combined pain levels 3 and 4, leaving us with subjects in no pain and some with more pain. After that, we then balanced the data set as there was a high number of no pain sequences, because we did this first by dropping long sequences of images first. Next, we padded the sequences to a length of 15, filling numeric data with null values, which would be ignored by the model. Inversely, we truncated any sequences over 15 images by starting at the end of the sequence. Lastly, we performed data augmentation, which rotated a subject's face by 10 degrees to the left or right. Facial feature extraction. To begin to process the images, we need to extract the numeric data from them. To do this, we employed the Inception Res NetP1 model, pre-trained on the VTG Phase 2 dataset. We used transfer learning on the MinPing dataset to recognize differences in our dataset, and we can then extract the 512-dimensional numerical embedding of someone's face. This is a compact representation of someone's face in an abstract manner. Also, an analogy to help is a fingerprint of somebody's face. Everything is very unique, and each person has their own line of code for their own face. After extracting numeric data, we appended the class, subject number, and sequence number to keep track of the data. Principal component analysis. Having 512 features in a machine learning model is too much data, and it would take up too much memory. To fix this, we need to apply PCA. PCA is a technique that combines features into a new set of uncorrelated features called principal components, or PC for short. They are linear combinations of the original features. A PC has something called explained variance, which quantifies how well the model captures the underlying pattern. So in figure 6, we can see that the first PC accounts for 14% of the variability in the dataset. We use the threshold of 95%, so when all of the 25 PCs are added together, it will equal 95%. As well as that, 25 PCs are logged, which causes longer computational times. For model testing, we had a 3-layer long short-term memory model with a single dense neuron for binary classification. The LSTM model is essential for sequential processing, which is why it was employed. The multiple layers allow the model to capture both complex patterns that span the entire sequence. The most right one was the one that captures the most complex patterns, while the ones on the left and the one in the middle are that capture the simpler patterns. So our results from the model testing included that we wanted the highest amount of accuracy score, but we also wanted a very similar validation training accuracy, so that if the AI or the machine learning model need to recognize new patterns, it wouldn't have trouble doing so. Having a very similar validation and training accuracy means that if new patterns show up, the machine learning model will likely have a better chance of understanding what that new pattern means. So what's most interesting is, if we look at from 0 to 20, the epochs from 0 to 20, the accuracy is much lower, but the training and validation accuracy are most similar, and we could use those. But what's most interesting is what's after epoch 20. If we look at epoch 27, which is where you have a crest and a peak, that part we have the most similar validation and training accuracy, and we likely would use that part, epoch 27, if we want to use it as a new model. It'd be the better model to select as training and validation accuracies are closer together. So, separate subjects. Even though our model was performing pretty well, it still had a very high computational cost, meaning it was really slow. This was due to the PCs, as there was 25 of them, which made a combination of several variables, making dimensionality very high. As well as that, we had straight and angled subjects, because we have people who were looking straight at the camera and some of them that were not looking straight at the camera, sometimes looking away from it. So some parts of that might be throwing our data and our accuracy off. And then we dropped the augmented images because they were rotated. While looking through the data set, we noticed that many subjects sat in consistent positions throughout the experiment. So that means that when they were taking images, most of them sat in the same position for all the sweeps and all the images for the different simulated pain. Some shifted around in varying position, so we decided to remove them from our experiment to reduce variability. For example, some people might turn from left to right, and that would affect our accuracy. After splitting the subjects, the explained variance more than doubled, and the PCs were cut down to 6 major variables, increasing our time. After dropping the augmentations and variable subjects, we were left with insufficient number of data points for training an LSTM model. So, a more diverse data set was needed. Emotions such as happiness and sadness are not included because it was unrealistic, and there were only males in this data set. Head position is important to the model as we saw an increase of explained variance. So, to handle this, because we were giving it to people who are elderly and they wouldn't be very understanding how to operate such an advanced type of model. So we made a GUI design which would simplify it for them. We presented it as sort of an app where they could select the different buttons very easily and understand what everything did without having to go in depth with trying to figure out what the complex parts of our program did. So with this, we have parts where we can insert images in or take images inside the app so that they can analyze it right there. As well as that, we use 2 different emotion models to do this. Going back to the idea, one of them used machine learning from different large directories of image and faces to detect different emotions, while the other analyzed the action units of the face and made a guess and assumption based off of that. So deep face was the one we used to directly analyze the face without having to go through the action unit part, while PY feet was the one that we used it to find the different muscles on the face, and it usually would determine something based off of that. Something interesting that I found with this was that with PY feet, it wouldn't detect teeth, so that made something that wasn't as good as deep face, although it was much more accurate than deep face as it could often see action units, which showed how the face tensed up and was better at analyzing things. So, something that we found was when we used the min-paint data set and we analyzed each of them to find action units and different correlations between the values, we found different interesting things that happened. Here you can see the progression of the muscle faces from pain level 0 to 4, and there's some interesting parts that you can notice. So, for action unit 11, if we go back to the slide for a second, it's the one on the mouth called the nasolabial deepener. You can see that it only appears in no pain, and whenever the subject's in pain, it disappears. So, there's also correlation between other action units, but it's pretty weak and it's not good enough to determine how much pain they're having. But one thing's for certain, we can determine that they are having pain or if they're not. So, with the accuracy, confidence, of motion, both language learning models had very low correlation and were not suitable to determine pain levels because each of them were emotional data sets, so they were not very suitable for it. But using the action units, we picked out the top 5 that had the highest correlation with the presence of pain. Using those 5, we managed to make the false negative rate of detecting pain or not pain to 0% because those are very accurate. So in conclusion, we developed a non-invasive AI-based technique and a framework and an accuracy score of 90.22% for validation accuracy about pain or no pain. However, there's a risk that this model will perform poorly with unseen data or something new that has not detected yet. Splitting the subjects by face orientation reduces the PCA, improving computational time. And for future work, We plan to expand the model to include a more diverse data set. For example, could include more people, more genders, and etc. We could also include other emotions like happiness or sadness, and create a model that has real-time processing capabilities. We can also develop a camera system that can self-orient to capture a consistent angle of the face, as this would solve the head orientation issue. We would like to acknowledge the New Hampshire Biomaid, and it's funded by the NSF Award. And do you guys have any questions?